I'm glad it's warmer today than it was yesterday, I think. All right, so here's our plan for today. We're going to work through the next section, probably the next two sections, because they're not that long. Again, a lot of what we're doing in this first chapter is kind of a review of what we did near the end of the first semester course, if you took that one. We're going to break for questions that you might have on the quiz material around 1:45. So if I'm still rambling, I'm letting you know that that's my goal, 1:45. So that if I am still rambling about whatever at 1:45, you can say it's 1:45, and I'll be like, oh yeah, that's right. And then we'll take our quiz. I do have a couple of extra calculators if people need. I don't know that necessarily a calculator will be needed on this quiz, but I have some extras if people need to use one. Ready to dive in?
Yeah.
Yes, okay. All right. So we're going to do some adding and subtracting of fractions. Last time we did multiplying and dividing. When you're multiplying and dividing fractions, you just make sure everything's factored, cancel what will cancel, and see what you're left with. When you're adding and subtracting, however, you have to have common denominators. Adding fractions with different denominators is like adding apples to oranges. I start with a really simple one. We already know how to do these, but just to illustrate the process and to tie it to something familiar, because the process with algebraic fractions is completely analogous. So I start by factoring the denominators. I don't really care about the tops right now, just the bottom. So 6 is 2 times 3, 15 is 3 times 5, and then I say, okay, I want them to be the same denominators, and I'm going to get them to be the same by throwing in any factors that might be missing. So I look and I say, what is missing from this denominator that is present in this denominator? 5. Okay, so it's missing the 5. I'm going to go ahead and add a 5 because I want to. I get to do it, as long as I also add the same factor up top. What do we need in the other fraction? 2. We need a 2, so we add a 2 on the bottom. Because we added a 2 in the bottom, we also have to do it on top. So now, rewriting these fractions, I have 25 over 30 plus 14 over 30. And when you have fractions that are the same denominator, you just bring that denominator straight over. And the operation, in this case addition, is performed just on the numerator. So 25 and 14 is 39. And then with any fraction, any scenario where we're giving an answer that is a fraction, we make sure that we reduce, right? So we could factor out a 3. 39 is 3 times 13. 30 is 3 times 10. We can cancel those 3's, and we get 13 over 10. So the way it works with algebraic fractions is pretty much the same. Should we try? Mm-hmm. Why not? Mm-hmm. Okay. So in example 115, these already have the same denominator, so I don't need to do any work there. I'm just bringing that denominator over. And then these operations, the addition and subtraction, will be performed on the numerators. I'm going to do that up top. So we have b plus 1 minus. Now we have to subtract the entire numerator, so I got to put parentheses around the 2b minus 1. Anybody else here who wasn't here on Monday? Not to blow up your spot, sorry. Okay. So the parentheses there are really important because otherwise, we make sign errors and stuff without it. And then we just do the algebra up top. So we have b plus 1. I'm going to distribute the negative. Minus 2b plus 1. Plus 1 because, of course, we're distributing that. Minus a negative over ax. And then combine like terms. So we have 2 minus b, or negative b plus 2 if you prefer. It's the same expression. I thought people might be more lively at 1 in the afternoon, but I don't know. We're bringing that 8 a.m. spirit into the afternoon. Maybe I am too. I don't know. Maybe it's me. Is it the weather?
I blame the weather.
Okay. All right, let's do some more. I'm going to sound excited. Okay. These are not the same denominator, so we have some work to do there. However, they're already factored, right? There's no addition or subtraction in the bottoms, so they're already factored. All we need to do is figure out what factors need to be added. I'm going to begin by just rewriting them, only because I think I'll need to use a little bit of room in between. I just want to build in some space. So what factors does the first denominator need to pick up? Yeah, it needs a 2, and I think that's it. No, actually, it definitely needs a 2, so I put a 2 on the top and the bottom, but it also needs an A, yeah.
And a B.
Oh, and a B. There we go. How about the middle one? It needs a 12. And an A squared, because we need to bring it up to A cubed. Oh, well, I think I'm bringing the 8 a.m. I'm making 8 a.m. mistakes, you know. Okay, now let's do the next one. What do we need here? A 3 and a B squared. I think you're right. Okay, let's keep going. Single fraction now with the common denominator. That denominator is, what, 12a cubed b squared. And now let's see what we can do up top. So the first numerator is 10ab minus, that's a minus because that's a minus, 36a squared. And then we bring down this plus, and 3b squared. And that's about it. I mean, there's no common factors that we could take out. So that's pretty much as far as we can go. If our goal was to add and write it as a single fraction, we have accomplished our goal. Let's do another. Here we do have some addition and subtraction. The first question is, if we're going to get a common denominator, I mean, clearly we could see that we don't have a common denominator. They are different. Let's begin by asking the question, what factor or factors does the first denominator need to pick up? What is present in the second one, not there in the first?
X plus 1.
X plus 1. Yeah, so sometimes people say, oh, it just needs like a plus 1 or something like that, but x minus 1 and x plus 1, those are prime. They're irreducible, and they are also completely different factors. So this needs to pick up the x plus 1. And what about the second fraction? That needs an x minus 1, yeah. So our common denominator is the product x minus 1, x plus 1. Now, I almost never, unless I have some compelling reason, I don't ever multiply this out because it doesn't get us anything. It's usually not particularly helpful. So I leave that denominator in the factored form. Our numerator so far looks like this: a times x plus 1 plus a times x minus 1. Now, I'm not multiplying out the bottom because it is factored. It is expressed as a product of its factors. The top, however, is not factored. I know it's not factored because of this addition in between. So for that reason, I'm going to expand everything. So we have expand everything on top. I've got ax plus ax minus a. We combine like terms, which basically, what do we got to cancel those a's, the plus a and the minus a. And then we have a 2ax. And that's as far as we go. Questions on that one before we try another? Okay. So in this example, we had some addition and subtraction in the factors, or in the denominators, but the initial fractions that we started with, the bottoms were already factored, and that's been the case so far in the last, our first examples. When that's not the case, if there is factoring to be done, that has to be our first step. So in the next section, or in the next example, the last two factors look pretty good. We can't factor them, right? The denominators, 1 plus 2x and 1 minus 2x. But the first denominator can be factored. How does it factor?
2x plus 1, 2x minus 1.
Yeah, because it's a difference of squares. So 2x plus 1, 2x minus 1. So, we always begin, if needed, the way we begin is by factoring denominators. 1 plus 2x is definitely the same as 2x plus 1, right? The order of addition doesn't matter. It might seem silly, but I'm just going to go ahead and write this in a different line. Now, in the middle, we have a 1 minus 2x. But over here, we have a 2x minus 1. So we have our factors where they're virtually the same, right? We just sort of reverse the order of subtraction. What can we do with that?
Take out a negative from one of them.
Take out a negative from one of them. And I think what I'll do, because we can reverse the order of subtraction just by factoring out a negative. So if we do that here, then... So if this is, so 3x plus 1 over negative 2x minus 1, like that. The other one I'm not going to take out a negative because that will result in the same, difference between those two factors. So I'm just going to do it to 1, so now it matches this one over here. And in the middle now we're subtracting what is a negative fraction, right? Because we have a negative in the bottom. So I'm just going to take care of that like so. Okay. Now, what do we need? What does the first fraction need?
Nothing.
Doesn't need anything. It's got everything. What about the second one?
2x plus 1.
It needs a 2x plus 1. And how about the last one?
2x minus 1.
Mm-hmm. So now we have the common denominator, so that just comes down with us. And again, unless there's some compelling reason, and for me usually there isn't, so that's why I pretty much never do it. I just, I'm not going to multiply out the bottom. That is factored, which is nice. We love factors. I love factors. Up top, what we have is this expression. So I got 4x plus, and then I have 3x plus 1 times 2x plus 1. And then I'm adding 2x times 2x minus 1. So the numerator, this is definitely not factored. It is not expressed as a product of its factors, and we can tell because of this addition in between. We're adding some products, right? I mean, this right here in the middle, like that is a product, but overall, this is just one big term of this whole numerator. So we have to start now by just expanding the top. We're going to do some foiling, distributing, and then combining like terms. So let's see, if we FOIL the middle product, what do we get? 6x squared. And then this would be 3x plus 2x, so that's plus 5x plus 1. And then distributing the 2x through these parentheses, we get 4x squared minus 2x over our denominator. So we have now 10x squared, 9x minus 2x plus 7x plus 1. Now what?
Or do we just leave it as that?
Well, we could. We can go a little further, though. I mean, when you are adding and subtracting fractions, or let me put it this way: anytime you're giving a result that is a fraction, at the end, our last step is a quick check: is this reduced? So we should check to see if that numerator will factor. So what do you think?
5x plus 1 times 6x plus 1.
And the reason, we check to see if the top factors, because then maybe we'll get to reduce. And a lot of the time, you can't. Like, a lot of the time, like, what you end up with, just by happenstance, ends up to not factor. But sometimes, it's worth checking. Sometimes we can actually simplify the fraction. So those 2x plus 1s will cancel. And this is equal to 5x plus 1 over 2x minus 1. Questions on that example? Okay. All right, so fractions within fractions, we call them complex fractions or just fractions within fractions. So there's a couple of different ways we could approach these types of problems. First of all, I think the most important thing to know is that fractions within fractions is not simplified. It's horribly unsimplified, in fact. So when we see fractions within fractions, our instinct needs to be like, oh my god, I am going to fix that, right? And then we set out to do it, which we're going to do right here. A couple of ways we can approach it. One way is to simply treat the top and the bottom like as its own problem, so I'll work on the numerator. Let's write that as a single fraction. So for example, this is, the first term is 1 over 1. And, oh, we should probably factor that denominator. That's a difference of squares, so we have x plus 1 times x minus 1. This is silly a little bit because, of course, I factor it as though it's not entirely clear that we're going to need to pick up the entire x squared minus 1, which clearly we're going to need to because the only factor down there is 1. But, you know, we have fun, I guess. So this looks like, what, x squared minus 1 over x squared minus 1 plus 1 over x squared minus 1. I guess we didn't really need to do that factoring. Factoring is thoroughly enjoyable, at least, so there's that. On the bottom, I know we haven't finished with the top yet, but just kind of carry this same idea through. That first term is a 1, which is 1 over 1. And so we can rewrite 1 as x minus 1 over x minus 1, because that is the denominator it would need to pick up from the second fraction. So now, working with the denominator still, bringing this over, how can we write this sum? What does that equal to?
X minus 1 plus 1 all over x.
Mm-hmm. Yep. Awesome. So, and the top, x squared minus 1. On top we have x squared minus 1 plus 1. We can simplify now. In fact, I'm going to bring this over here. X squared minus 1 plus 1, right? So working with this fraction, these guys will cancel, the minus 1 and the plus 1. Likewise, the same thing happens on the bottom in the numerator. So like the minus 1 plus 1 cancels. So we have x squared over x squared minus 1 over x over x minus 1. So the whole idea behind this technique is that if we work with these fractions and write the top and the bottom each as a single fraction, then it turns it into like those problems we were doing on Monday, like where we're just dividing fractions and we know that we can turn it into a multiplication problem, factor, and see what cancels. So this would be x squared over, so now I am going to just factor that x squared minus 1, x plus 1, x minus 1. And then we will multiply by the reciprocal of the bottom, x minus 1 over x. Now is the fun part, where we whip into a frenzy of canceling, and we're left with x over x plus 1. So that is one technique. This technique often takes a little bit longer than the other technique. They both work very well. They both work equally well. Really, it's just a matter of kind of how you like to approach the problem, what you feel more comfortable with. So just to show you the other technique here, in the space we have left, I'm going to rewrite this problem. We had 1 plus 1 over x squared minus 1 over 1 plus 1 over x minus 1. The other technique says, the way we go about it is we look at this and we're like, okay, of all the fractions that I see in this overall big fraction, what is the least common denominator?
X squared minus 1 times x minus 1.
It's actually just the x squared minus 1 because, and I'll show you why, so I'll go ahead and factor that. It factors, and it actually, this already has So the LCD is x plus 1 times x minus 1. And so in this other technique, what we say is, okay, I'm going to multiply the top and the bottom by this LCD. The top and the bottom of the big fraction. Which is a totally legal move. Because you're allowed to multiply the top and the bottom of a fraction by the same thing. And when we do that, now we can distribute through these parentheses. So now we have x plus 1 times x minus 1 plus what happens when we distribute to the second term, to that fraction. Just turns into 1 because these denominators all cancel when you distribute there. What happens, what do we get on the bottom? You end up with what? Okay, well, so we're going to distribute to the first term, right? So I'm going to distribute to the 1 here, so we get x plus 1 times x minus 1. And then what happens?
We end up with x plus 1.
Yeah, because what happens is the x minus 1s will cancel when I distribute this to this fraction. The x minus 1s will cancel, and we're just left with the x plus 1. And now all that we do is expand and simplify the numerator and denominator. So we have x squared minus 1 plus 1 over x squared minus 1 plus x plus 1. The minus 1 plus 1s cancel because they're terms. And we have x squared over x squared plus x. We can factor out an x on the bottom. And when we do that, we can cancel a factor of x. Of course, we're not surprised to get the same result as when we did it the other way. All right. You want to do another? Okay. So this is what I like to describe as like a sneaky complex fraction. This is somebody writing down a fraction and saying, I just don't want to do the algebra. Maybe nobody will notice if I sneak in fractions within fractions by using a negative exponent. But we, of course, notice, negative exponents are fractions, right? 2y to the minus 2 is 2 over y squared. That's what the negative exponent means. It means this stuff goes on the bottom. So the first step here is in recognizing that we do in fact have fractions within fractions, and I'm going to begin by just rewriting the fraction to make that explicit. So let's try that other technique. If we look at the fractions present here, what is the least common denominator? Xy squared. So I'm going to multiply the top and bottom of the big fraction by xy squared. And then we're going to distribute. So I think I'll just write them out. 1 over x times xy squared. And I'll go ahead and just write it as xy squared over 1, just to kind of make it easier to organize. Do the same thing on the bottom. And then we just simplify each of those fraction products. So let's cancel stuff that will cancel. These x's are gone, and then these y squareds are gone. Similarly on the bottom, those x's cancel, and then in the other fraction, the y squareds cancel. And what we're left with on top is we have y squared plus 2x over y squared minus 2x. Can we cancel anything? No, they have no common factors, and we don't cancel over addition. That is the cardinal sin of algebra, canceling over addition. Moving right along. We'll look at how we solve equations with fractions. Now, our technique for, when we solve equations with fractions, usually we're working with equations that involve adding and subtracting fractions. So we're still going to be really interested in what the least common denominator is, but our approach will be slightly different. You can approach it by actually doing any addition and subtraction and getting common denominators. That's usually a lot more work than is necessary to get the job done. So I think the simplest way to approach this type of problem is to just identify what the LCD is, right, and then multiply each term by the LCD. In doing so, you guarantee that you will be able to cancel every single denominator, and then in your next line you have an equation with no fractions, which is awesome. So let's start out with a simple-ish one where our denominators are constants. What is the least common multiple of 12, 8, and 6?
24.
24. Okay, so I'm going to multiply both sides by 24. This is the algebraic move that we're allowed to make, right? We can multiply both sides of an equation by the same thing. I'm going to actually write out in practice, usually the way I begin these is I start by writing the equation with plenty of space and just saying, okay, I'm zapping each term with that factor of 24, 24 over 1. We're allowed to just do this because it's what stems from this step, right? If we distribute the 24, we will get exactly this next line. We multiplied by 24. Now, sometimes what people will do, they'll remember that, oh, okay, I've got to find the LCD and multiply through by it. But then sometimes people will get excited and they'll distribute and multiply this way. The whole reason that we chose to multiply by 24 is because we are guaranteed, we know everything can cancel with it. So go through and cancel all your denominators. 12 goes into 24 twice. 8 goes into 24 3 times, and 6 goes into 24 4 times. So now we have 2x minus 3 equals x plus 2 times 4. Now 4 is being multiplied by the entire x plus 2, so we need parentheses. So we have 2x minus 3 equals, we're going to distribute that 4. It's just a linear equation, right? We've solved it maybe, I don't know, a million of these. Distributing the 4, we get 4x plus 8. No. We should probably solve, not just write down the same equation again. Let's get our x's on one side. I'll subtract 4x, add 3. So we have minus 2x equals 11, and now it's all over but the shouting. We get x is negative 11 halves. How's that so far?
Good.
Okay, good. All right. Next example, what is the least common denominator here?
Is it 2n plus 2?
No.
Okay.
2n times n plus 2.
Yeah, 2n times n plus 2. So, one denominator is 2 times n, so I need a factor of 2 and I need a factor of n, and the other one is n plus 2. So we're basically just grabbing all the factors that we see. So we can just multiply both sides by this product. We do this specifically because it allows us to cancel all denominators. So let's go ahead and cancel. On the left side, the n plus 2's cancel, and on the right side, the 2n cancels. So now we have 2n times 5 is equal to 3 times n plus 2. Now one thing I want to point out here is this is, because of this type of equation, because this equation was simply one fraction on one side by itself, another fraction on the other side by itself, this is actually a proportion. So you could have started out simply by setting the cross products equal to each other. Like 3 times n plus 2 is the same as 2n times 5. That is exactly what we get here. The reason the whole cross product thing works is because it's what you get if you multiply both sides by the LCD. So we have 10n equals 3n plus 6. And a nice linear equation to solve, so we can subtract 3n. And then divide both sides by 7. Let's keep going. Last page. Okay. What is our LCD here?
3x.
Yeah. So our LCD is 3x, so let's zap everything with a 3x. What comes after this?
Get rid of the x and x.
Yeah, do all the canceling we can do. So these x's cancel, on the other side, those x's cancel, and then the last fraction, the 3 cancels. And so we have 3 times x minus 3 equals 3 plus 2x. And a nice, another linear equation that we totally know how to solve. Distribute the 3. You can subtract 2x and from both sides and add 9 to both sides. So we get x equals 12. Questions on that example? Okay. One more. What is our LCD here?
X times x plus 2.
X times x plus 2. Awesome. This first term, of course, just is a plain old 2. That's 2 over 1, which is why that doesn't contribute anything to the LCD. So I'm going to just write out this equation, leaving me space, because I know I got to write in some factors to add. We've identified the LCD. The next step is multiply each term by the LCD. So multiply by x times x plus 2 Why do we multiply through by the LCD? Say that again?
Try to cancel stuff.
Yes, because we can cancel stuff. Nothing to do on the first term, but on the left side on the next term we can cancel the x's, and on the right side we can cancel the x plus 2. So now we have 2x times x plus 2 minus parentheses x plus 2. I'm being really careful about that because we're subtracting that entire x plus 2. We're going to have to distribute that negative sign. On the other side, we just have 3x that we're left with. So we've got 2x squared plus 4x minus x minus 2 equals 3x. Let me get everything on one side. I'll subtract 3x. So we have 2x squared plus plus 2x. Minus 2. Oh, wait. No. The x cancels out. Just making sure, you guys. No x's. As it turns out, okay, sometimes we learn big lessons in this class. Today's big lesson is 4 minus 4, 0. Not 2. Yeah. All right, this one's not linear. It's a nice quadratic, but we have a couple of different ways we could solve this.
Pull out a 2 in factor.
We could pull out a 2 in factor. So if I pull out a 2, and we have x squared minus 1, pulling out a 2, the remaining factor, x squared minus 1, that's a nice difference of squares. So let's factor that. I love factoring. Now, if a product of things is set equal to 0, what do we know?
If you have 2 answers.
Yeah, in this case. More generally, though, if I multiply two things and get 0, what has to be true?
One of them has to be 0.
One of them has to be 0, and that's why we get two possible answers here. So, if this product is 0, first of all, we know 2 is not 0, so that's not going to give us a solution. But we get x plus 1 is 0, or x minus 1 is 0, which gives us our answers of -1 and 1. So as it turns out, this has two solutions. One of the things you always want to check, and I didn't talk about it very much in the previous examples, but if you're solving an equation with fractions, one thing you want to check is that they are actually solutions. Not that the arithmetic works out, but that the only thing you need to check here is that it doesn't make you divide by 0. So if a value of x that you get for a solution makes one of your fractions like something divided by 0, then that is actually not a solution. As it turns out, we're fine, right? If x equals 1 and x equals -1 does not make any of these doesn't make any of these 0. But it's one of the things you just want to check. If I had gotten like x equals -2 as a solution here, I would look up here and be like, uh-oh, that's going to make that fraction 0, and I just cross it out and say it's actually not a solution to the equation. All right, that's a good day. So we finished the first chapter. It's a nice sort of review of our one of my favorite things. I love factoring fractions. I don't know.
We even got done before 1:45.
I know. I could sit here and just ramble for another 3 minutes and still be on time. So let's go ahead and take some questions now. I don't know if you all had any questions on the practice exercises.
6.6, number 23.
Six 6.6.
6.4.
So 6.623 and 6.419.
Yeah, because
I should probably bring my actual book because they switched up my electronic edition to the SI units version, which most of it's the same, but let me see. Is 23 the one that looks like x to the fourth minus 1 on top?
Yeah.
Okay.
And then x plus 16.
All right, so we're going to multiply. This always begins by factoring, right? So sometimes people look at these and they're like, okay, multiply. Let me just start foiling everywhere and be like, no. Like, factor, cross stuff out. So the x to the fourth minus 1, that is a difference of squares. How can we factor it?
X squared plus 1 times x plus 1 times x minus 1.
Yeah. That's how it looks fully factored. The intermediate step is, right, like the difference of squares will end up looking like this. And then we say, oh, that's also a difference of squares, and then we break that up. On the bottom?
You take out the 8.
Yep, and we get,
X plus
yes. How about in the over on the right?
take out the 2x.
Take out a 2x, and what are we left with inside?
X minus 4.
X minus 4. And on the bottom?
Like x squared plus 1 times.
Just times x, I think. Yeah. Yep. Yeah, so we just take out the x. There's the common factor, greatest common factor. So now we've done all the factoring, and we can whip into a frenzy of canceling. The fun part. The x squared plus 1s will cancel. The x's cancel. And the 2 and the 8. And I think that is it. So now we have x plus 1, x minus 1, x minus 4 on top, and on the bottom 4 times x plus 2. Yay. Victory. All right, and so the other one, 6-4, number 19. This one looks like 0. They just want us to factor 0.001 r cubed minus 0.064. Okay, big R cubed and then little r cubed. That one?
Yeah.
Okay. So one of the things that makes this one a little tricky is like the decimals. And we're like, I see the cubes. It's in the sum and difference of cubes section, so I'm kind of like angling toward that. So to make things easier for myself, usually I look at that and I say, you know what, I'm going to factor out a 1/1000th. Like, I mean, this is 1 over 1,000, right, as a coefficient. This is 64 over 1,000. So if I factor out 1 over 1,000, then in the parentheses I could write just big R cubed minus 64 little r cubed. And now that one seems a little bit more manageable to factor. So we get let's see, difference of cubes is the one, we have a little factor and then a big factor. 64r cubed is the cube of, what's the cube root of 64?
4.
4. Okay. So what's our little factor going to be?
Minus 4r.
Yeah, big R minus 4 times little r. Yep. And now what does the big factor look like?
R squared.
Uh-huh.
No, you can go ahead.
Plus 4 big R, little r, plus 16 little r squared.
Yeah. Yeah, so a big R times a big R, and then in the middle we do one of each. So big R times a 4 little r, and then at the end, 2 factors of the force, 4R times 4R, or 16R squared. Other questions? No? All right. Would anybody like to borrow a calculator?